My name's John Holler. I'm the CEO, and it's a pleasure to have you here today for another in our series of events, not just lunches, but events that are designed to coincide with the 50th anniversary of the invention of the integrated circuit and the growth of the semiconductor. For those of you who showed up today, knowing that you were going to hear about programmable logic, you are here because we have one of the best people in the field to talk about it, and we aren't afraid to get a little technical at lunch as we do that. Steve Trimberger holds more than 150 patents in programmable logic devices. He has chaired numerous steering committees and blue ribbon industry committees in the field. He's written 3 books on design automation and field programmable gate array technology, the famous FPGA industry. But you probably know Steve because he's a Xilinx fellow. He's led many, many breakthrough FPGA projects since joining Xilinx in 1988. He was a member of the technical architecture group for the XC4000 FPGA, a technical leader for many other segments of that whole field at Xilinx, and he managed the Xilinx Advanced Development Group for many years. Steve is really sought after to make the presentation that he's going to make today. And after he does that, Stephen Smith, who, as I just found out, once shared a cubicle, or was across a cubicle, I guess, from our speaker, is going to be up here to conduct the question and answer session. So we'll have Steve's presentation. You have question cards on your table. Please fill those out. We'll be collecting those about 1/4 to the hour. Stephen will be coming up here for the conversation and the Q&A. And please just feel free to ask as many questions as you like. So it's now my pleasure to welcome our guest for this lunch, Steve Trimberger.
Thank you. Well, it's quite a pleasure to be here at the Computer History Museum. One of my favorite places to visit, down in the visible storage room. You get to stand in back and listen to the comments, and not just the comments from the docents. Basically, you hear comments like, oh yeah, I've got one of those in my garage, sort of the spouse's lament. But what I really like to hear is people start talking about these machines they know. And it's exciting to me because I started programming computers before the homogenization period. Back in the 70s, we had interesting machines, and you hear these comments like, "Oh yeah, that was a decimal digit serial machine," or "Did you know this machine has 36-bit words and you can break them up into 6-bit bytes? There's an 18-bit address field with an indirect bit, and if you jump indirect to yourself, it puts the microcode in an infinite loop." Now, all this interesting stuff you really need to know about old hardware. And then Moore's Law came along, and well, the reason for all these interesting old machines was that not that they were so silly, but they were efficient. They were targeted to a specific thing. If you wanted to run payroll, maybe you wanted decimal digits. If you wanted to do ballistic trajectories, you have a specific word size for your arithmetic in mind. And so these machines were efficient, but once Moore's Law kicked in, well, you could get a 2x performance improvement just by sitting on your chair for a couple of years and let the process engineers turn you into a genius. And so many people made a living at that. And then, but we're sort of in an area where we think maybe that's slowing down a bit. So I'm going to talk a little bit about computers, and keep in mind these old machines because I think they're interesting. So computing bit by bit. First, I get to brag a little bit. Oh God, another pun. So this year, IEEE and Spectrum magazine announced their 25 microchips that shook the world. And one of them was the Xilinx 2064 FPGA, Field Programmable Gate Array. I'm going to be using the term Field Programmable Gate Array, FPGA, and programmable logic pretty much interchangeably. And I saw a couple out here in the audience who would probably object to that. Sorry, guys. It's my talk. But so what is about this machine? Why was it honored along with the 8088, Z80, ARM1, SPARC, 6502? What is this thing? The field programmable gate array was designed as a replacement for custom logic. Back in 1985, if you wanted some custom circuitry, you could contract to have it built yourself, go through the manufacturing cycle, and buy yourself a few thousand or a few tens of thousands, or if you wanted to be economical about it, a few millions. But if you had low volume, maybe that's not a good idea, or if you didn't really know how to design integrated circuits, maybe that wasn't a good idea. And so to reduce the risk of all that, save money and time, you could buy this previously built thing and customize it yourself. This was not the first programmable logic device. What was special about this? It was special because it was programmed by writing into memory on the device. And you could overwrite that memory, and you could change it. This was determined, the marketing department at Xilinx decided this was an extremely bad thing. They didn't want to publicize this at all. The reason was our competitors were talking about volatile logic. Where does your logic go when the power goes out? You know, it's hiding under the circuit board. I don't know where it is. So this was the problem. It really had two big advantages. One was in test, that we could program it and reprogram it, and we knew that a device that we shipped would work. The other one was in manufacturing. In a new process technology, the first things you're able to do are wires and transistors. And if you can do that, you can do memory and logic, and you can make this device. If you had to wait until you had a fuse or an EEPROM structure, that would take longer. And so this allowed the company to target new process technology, take advantage of Moore's law earlier. It also allowed us to trade off manufacturing partners against one another, which was also valuable early in the life of the company. So over time, so where are these things really used? I can get this to work. Well, Xilinx has about over 20,000 customers. So programmable logic, this customized logic, is used nearly everywhere. I'm not going to go through the list of applications. How is it used? Well, it turns out despite having this ability to reprogram, easily 90% of the devices only get programmed once. They're doing things like, well, we called it glue logic. Oh, I have a keyboard that's producing 108 different signals, and I needed to encode that. Or I've got a memory that's got a different voltage than my processor. Or I've got a display device that needs some buffering. Variety of problems like that there's no custom, no standard product for that. You need to build that. But it also gives another advantage. You can upgrade this product, this hardware product, in a similar fashion to where you would upgrade a software product, and for the same reasons. So you could have Rev 1.0 of your display driver, and then 1.1 and 1.2, and even if you're not updating them in the field, you could at least charge money for somebody to buy the next one. So being able to program and reprogram wasn't essential to the technology, but it was to using the technology, but it was very useful in the product life cycle. And that's another aspect I'm not really going to be talking about. But I really want to jump into, well, I got the go-ahead to say something a bit technical, so let me talk a little bit technical, and I'm not going to go real deep into this, and there won't be a quiz, so don't worry about that. So how does this really work? It's not quite black magic, but it's probably more brute force than you imagined. How do we make logic that's programmed by writing into a memory? Easy. You build a lookup table of the memory. And I have this red lookup table. It's 64 words of 1 bit. Okay, that's funny-looking memory. Yes, we build funny-looking little memories. But when I do that, I have a 6-bit address. I can address any one of those bits. And if I think of my address as independent signals, then this lookup table is the truth table of the function. So I can have absolutely any function of those 6 inputs just by writing the right pattern into the lookup table. Okay, so what are some interesting patterns? Well, parity might be a good one. I could look at this and say, well, I have 2 of these inputs, and those are the select lines, and the other 4 are inputs, and I have a 4-to-1 multiplexer. I can build that in its function. Now, those of you who are thinking about, gee, if I were to design a 4-to-1 multiplexer on my own at home, I could do this a lot cheaper than 64 memory cells and a big multiplexer, and you're absolutely right. This is tremendously inefficient in its use of transistors. And guess what's been happening the last 20 years? Transistors got really, really cheap. And so it may be inefficient in the use of transistors, but transistors are pretty cheap. That result I can pull out and I can use it immediately, or I can put it into a register and clock it and use it next time. And something that turned out to be very handy, if I build an exclusive OR, excuse me, in that lookup table, I can compute the sum, and I build a dedicated carry logic, and I have 1 bit of arithmetic here. Okay, 1 bit of arithmetic doesn't sound very exciting. Well, I can gang them together, and I can make 8, 16, 32. I can make 2,000-bit arithmetic. I can make 6-bit arithmetic. I can make buses of any width I want. So if I need a bus of 2,000 bits, I can make that. Run it into an adder of 2,000 bits, I can make that. Or I can build hundreds of smaller arithmetic units or logic units. So I can build a custom computer, or more interestingly, a custom execution unit. Okay, so how much can I really do? From those early beginnings, what we have today is we have about 500,000 of those logic cells. A large device contains about 9 megabytes of memory. It's not 1 block of memory, it's 2,000 small memories, each independently addressable. 2,000 memories running at 500. I got terabytes of bandwidth inside this device, in and out of those memories. Microprocessors, oh yeah, there's a couple of these are 2-scale. So if you throw on a microprocessor with its cache, it's really not that big on this device. It's 2 billion transistors, along with all the rest of the interfacing and so on. Now, this is the large battleship device. So we actually make a family of devices, and they're smaller ones, and basically what customers wind up doing is they buy their logic by the yard. How much do you need? That's the size device I'll buy. So let's talk a little bit about computing and a specific computing problem that's faced by some people just down the road in Mountain View. The SETI Institute is building a radio telescope. Now, radio telescopes, you want to collect as many photons as you can. One way to do this is build just a really large dish of metal, and that's been done. The problem is, as these dishes get bigger, the cost of the steel gets astronomical. And the alternative is, instead of making one great big dish, you make a whole bunch of small dishes. If you make a whole bunch of small dishes, then you have these little problems. I got to bring all the signals together, and I got to correlate them. Well, first I got to offset for the speed of light between the dishes and bring the signals together. And now this correlation problem, though, is basically there are Fourier transforms. I've got an n-squared kind of problem here because I've got to correlate every dish with every other one. So as you do smaller dishes and more of them, your steel costs go down, but your electronic costs go up. Okay? So where is that point? Well, the Allen Telescope Array currently has it has 42 dishes working. Okay, 42 dishes. And if you look at the correlation problem, you could run out that calculation, and they're doing about 4.7 tera multiply accumulates per second to correlate their data in real time. Okay, so that's a few 100,000 processors, something like that. It's currently being done in 16 FPGAs. They could have done it in 4, but they saved a little money, actually. But if you were to do this in the actual telescope they're building, the plan is to build 350 dishes. This is 300 teraops per second. Estimated to take a couple of hundred FPGAs. If you were going to do this with more traditional microprocessor technology, this would be about $1 million a month in electricity. So if you build a custom supercomputer, which is what they're doing, you can get by with many orders of magnitude improvement in performance and in power. how do you do it? I've got a couple more slides. This is introducing a little difference in viewpoint. How do I get 1,000-fold increase in something that's running a few, maybe an order of magnitude slower clock rate? In traditional sequential processing, this is actually a simple example of a simple filtering application. If you do this sequentially, I multiply, I add, and I multiply and I add. And then if I'm doing 640 taps, I can do 640 cycles and get an answer. But if I can make more multipliers, if I have as many multipliers as I need, and I have an adder that takes in as many inputs as I need, and there are ways around that too, but I can get this, then I can get a result out every cycle. So I can get a 600-fold increase here by going parallel. I get a 600-fold increase in the amount of number of multipliers I've got. And I've got to have a system that's going to support that. That didn't look too much like computing, but let's look at something that does. Okay? So here's a bit of a DES application code, and I've got this green array of rectangles. And this is my logic array. And in this application, I've got the few operations. For example, that let's ignore the outer loop for a moment. That's temp 48. The expand operation is taking a 32-bit value and making a 48-bit value. So it's duplicating some bits and moving them around. Well, that's easy in this technology. To move bits around, I just wire them to where they belong. There are no operations required. If I needed to go to two different places at the same time, I can wire it to two different places at the same time. No operations required. This, the blue part, these are 8 different lookups in small lookup tables with small addresses. And there's a lot of activity there, masking out bits and shifting bits. Again, this is just moving the bits around. This requires no logic. So in this device, in this application, the blue S boxes turn into the blue regions on the device. I can build those out of the lookup tables I've got. The exclusive OR operations and the rotate, which actually does a select, fit into those 6 input lookup tables that I had. And so I'm doing all these operations. I have small bit operations I've replicated. I have movement of data that it just evaporates out of my logic because it's just, I can wire them to where I want. So I built sort of a custom shuffle operation there. Basically what I'm doing is I'm building a custom computer for this application. And I don't need to stop here. I could unroll this loop. If I unroll this loop in space, I replicate it. This loop has a loop carry dependency. This loop has a result, each iteration requires the result of the previous one. So what do? I pipeline, I save that register. I don't have to push it anywhere else to save it. Remember those registers that I had on my lookup tables? I save it there. And so now I'm flowing data through this machine. Replicating, taking advantage of small bits, small word sizes, small byte sizes, and deep pipelining. How deep can you go? I was looking at a presentation from Michael Flynn at Stanford recently, and he had an application. He was doing oil and gas exploration. So 30,000 sensors, they're pinging this about every 10 seconds. 468 deep pipelines, 468 deep latency, 8 lanes. It's only running at 250 megahertz, but it's a teraflop. These are floating point operations in 2 FPGAs. So you can make arbitrary wiring, arbitrary busing, build a custom supercomputer for your example. One other application we can do with something that's pretty clever is partial reconfiguration. So yeah, we can reprogram the devices, but you can reprogram part of it at a time while the rest of it continues to work. And that operation can be managed internally. We weren't the first ones to think of this. The first reference in the literature I found to this partial reconfiguration or this dynamic reconfiguration was by a researcher named James Blish in his Cities in Flight novel. from the 50s, where he had computers rearranging themselves to solve new problems. Of course, his computers rode on railroad tracks, rumbling around in the basement of the building, and you had to keep out of the way when they were doing that. We've made a little bit of progress since then. So if you have these pieces, one interesting application is a software-defined radio. You have your cell phone, but maybe you would like to be able to do push-to-talk, receive GPS signals, Wi-Fi when it's available. You would like this machine to even perhaps bridge these different networks, or serve as a router in case of emergencies. So these are applications, and you'd like to not have to carry around 6 different radios, and you'd like to have to not carry around one device that has 6 different boards in it. And so just as you can reprogram the software stack to manage the different protocols, you can reprogram the programmable logic stack to manage the different encoding and error correction schemes and security schemes of these different mechanisms. So we get back to this question, is it computing, or is it just emulating computing, like some science fiction writers have said computers would emulate emotions or emulate true intelligence? I don't know, maybe we could apply the Turing test here and say, well, if it's something that we would ordinarily think of as computing, but now it's done in a programmable logic device, that's still computing, and yes, it's doing computing. We have done several applications that were done on more traditional computers, but we needed a custom supercomputer to do that. It brings up the question, what is a computer? So one aspect of a computer is the processing element. And I've contrasted a microprocessor processing element with a spatial programmable logic device processing element that can both actually transform input data to output results. Another component of what is a computer is the system component. And I highlight this by saying, well, you know, your microprocessor, pick it, can't download a web page. It can't run Word. Why not? Well, there are a few other things it needs. It actually needs an interface to the network, and it's going to need the memory, and it's going to need a BIOS, and a bunch of things it's going to need in there. That system, the rest of the box provides all that stuff. That's actually been an area where programmable logic, these spatial computers, have been weak. We've built these machines, and we haven't built the appropriate environment around them. One of the successes of the PC industry today has been the success of not just the glorious microprocessor, but that whole system that allows you to use that processor effectively. So there's an interesting work going on in actually the cubicle next to mine, and taking a large FPGA, putting it on a board with a physical interface it matches the Xeon processor, sticking in the server, and talking, well, FSB, but now QPI, getting access to that whole system. So now one of your slots in your server is a custom supercomputer. Probably the weakest point in the whole programmable logic development chain, or the spatial computing development chain, is programming. We are very comfortable in our computing industry with a programming model that's a sequential flow of control. That's not the programming model that we have in the programmable logic business. Remember our history. We come from hardware description. And so our programming language, though it still looks like characters, we have these languages, VHDL and Verilog, but they are not simple sequential programming languages. They leverage Boolean algebra, but they require explicit serialization and explicit synchronization. So much of that is hidden in today's programming languages for sequential computers, but that's a flexibility that's required to get the performance out of spatial computers. We also have this problem with proximity and speed. Timing isn't guaranteed. So you do your program, you set up you build your custom computer, and then you find out how fast it runs. Well, this doesn't agree well with a lot of people. So what are we doing in programmable, in programming languages? Actually, not surprisingly, there's a tremendous interest in C or C-like programming for spatial computers, for programmable logic devices. To date, they haven't been particularly well received because they haven't given particularly good results. And in fact, they haven't given particularly good results because they're being compared with a hardware description mentality. Gee, how good is this compared to what I could do if I were sitting down and thinking about all the problems myself? And so, but there still have been some interesting successes. It depends on how much of that problem you extract away. In last year at the Memo Code conference, there was a competition. And using a high-level language, how much can you accelerate this problem? And the problem was not one of these signal processing, how much can I shove through the custom computer. The problem was retrieve data records, sort them, and save them back. The wrinkle was the data records were encrypted. So you had to retrieve data records, decrypt, sort, re-encrypt, save. So the winning team from MIT used a language called BlueSpec and achieved 1,100 times improvement over standard processor. And this was not designing it like hardware, this was designing it like software. Their software was able to take that C specification, or close to C specification, and insert the parallelism, the pipelining, and those operations we talked about earlier. So while programmable logic is headed toward a more sequential type specification because of its ease of use, something to do with human psychology, I suppose. At the same time, we note what we have our sequential processors, our temporal processors, looking to multi-core and many-core, and having to deal with this same sort of parallelization problem that the programmable logic of spatial computers have been looking at for years. So while the spatial computing is it's inching its way toward temporal computing is inching its way toward spatial for the performance advantage. We're going to meet in the middle. I don't know where in the middle, but we will meet in the middle because there's nowhere else to go. Thank you. And I'd like to invite Stephen Smith up here, and we'll take some questions.
So Steve, I'd like to start off with the first question I was given. You talk a lot about bitwise computation, but what about word-oriented FPGAs? Do you see any future in that?
What about word-oriented FPGAs? So what matters is what structure does your problem look like? If you start with a word-oriented kind of model, then yes, word-oriented FPGAs make a lot of sense. But a lot of the applications that I've seen, especially, have worked with very small bit sizes, and some of the high performance has come from exploiting the very small sizes. So that's been pretty successful. There have been commercial ventures for word-wise. Might not call them FPGAs, or maybe they're just avoiding the terminology. For whatever reason, no commercial success yet.
Right.
Part of that may be, as I mentioned, the programmable logic. The programmable logic doesn't exploit the computing aspect of this. It's not a large segment of the business. And so basically what's happening is all those people buying their programmable logic devices as ASIC replacements, buying them for just doing custom logic, are subsidizing the computing field right now. And so there may not be sufficient business until the software matures enough in order to do that.
That's a great answer, thank you. So this is a great question, actually. Can you tell us about the next great leap in the field that you're most excited about?
No. I guess not.
Okay.
Actually, the next great leap in this field has got to be in the area of design technology, design methodology. We've made great strides in exploiting Moore's law to produce just bigger devices and faster devices. When you look at that slide I had on what a modern FPGA looks like, you say, wow, I've got a couple of power PCs, I've got memories, I've got Ethernet Mac. Designing this thing it's not just sitting down and figuring out what connections I want or what logic I want. There are these system design issues that we really don't have a good handle on, and there are a few people in the world who seem to do this very, very well, but there aren't 20,000 of them. We'd like to have at least 20,000 of them and make them our customers.
Okay. You mentioned Moore's law quite a few times. So when do you expect an end to Moore's law? And as we approach the end, if there is one, what's FPGAs doing about it?
So when is the end of Moore's law? So do I need to go on record as for this one? So far, everyone has been wrong. I might as well be wrong too. I expect it to last until after I'm retired. And there may not be independent efforts. So what are FPGAs doing about it? Interestingly, FPGAs have leveraged Moore's law pretty heavily. And we compete against custom logic. But as I pointed out, we take about 30 times or 50 times as much logic to implement something that would you have if you actually built it directly. So if I wanted one gate of logic, it takes a programmable device about 30 gates to do that. Well, that's a big deficit. There has to be a big advantage. Well, programmability has been a big advantage. But the other thing we use is process technology. So we're very aggressive on process technology. Not quite as aggressive as Intel, they're kind of a class by themselves, but compared to our competition for custom devices, we generally stay a generation or maybe two ahead. That doesn't make up a 30x deficit, but it does mitigate that. And so as Moore's law, should Moore's law come to an end, this is a problem for us because it says the gap we have from being aggressive now starts to close. On the other hand, how would Moore's law end is an interesting question. Does it end by, well, one generation you'd stop getting performance improvement, and the next generation you stop getting power improvement, and the next generation you stop, gee, if it ends in dribbles like that, well, maybe programmable logic has a lot to offer in that case. If it ends as we have difficulty manufacturing something, and it comes out highly defective, well, programmable logic, by its nature, has a lot of redundancy in it. I put an adder in one block, I could put it in another one. No big deal. So you could avoid the errors, you'll avoid the defects in the parts while you build your custom supercomputer. Okay. Doing this, mapping to non-defective regions of your device has been done before. There are actually some, HP Teramac did this over a decade ago. Very, very effective. You can use parts that have a lot of defects in them and never notice it. Sort of like hard drives, right? You have hard drives with a lot of defects in them, but you never notice it.
Okay, thank you. This question is an excellent question coming up. Why are the FPGA bit file formats proprietary? And why not publish them like the instruction sets of a general purpose processor?
Did you set me up with
I
this
did
one?
not set you up with this one. Someone else did.
Thank you, whoever did that. I love talking about this topic. And you may have to stop me. We might run out of time. So why are they proprietary? They're proprietary because it's work to make them non-proprietary. So if we were to publish it, we would have to tell everybody what it does. And honestly, yes, we do know what everything does. But to put that in a form that everyone else could use means a documentation effort. Okay, so now why is it we don't think that documentation effort is worthwhile? Actually, I should take this back. And we did this once. We did this with the 6200. So we published that format. And that was a particularly easy one. It was a very simple format. So why is it not important? What would you do with it? Okay, so what would someone do with it? Well, if someone could write their own software, I suppose. Well, that's wonderful, and we have people who do that. The bit file is that last bit of translation from I know what I've got, I know where I've put it, to precisely how do you code it. It's going from assembly language to machine code. So it's not a big task. We have tools that do that. Frankly, the tools that we have that do that are pretty darn cheap. And so there's not a lot of perceived value in putting everybody, publishing that, putting everybody in that business. We also retain the ability to change it by keeping it proprietary. We haven't done it often, but we've done it occasionally that the bit file has changed. And of course, nobody notices because they never look at that. So we'll stop here.
Okay, thanks. Getting back to your application of SETI, is the SETI dataset streamed or in real time, or is it stored and computed offline? Can you comment on that?
It's streamed in real time. There are plans to store that. Actually, there are several very interesting plans going on. You should really talk to those guys. So one plan is to actually retain a buffer of maybe several minutes or up to an hour worth of data. So if you see something interesting, you can go back in time and look at it again. So that was pretty clever. There's also a plan to save snapshots of the data, but there's so much data that it's just hard to save that and do anything sensible with it. They have this real problem. So they have a huge amount of data, and it's on the top of a mountain. So even if you could get all the computers up there, you couldn't get the electricity up there to do it. So if you were going to store this in a big storage server and then put it on the back of a truck and truck it to San Diego, as has been proposed, then you'd actually need a truck about every 2 or 3 miles down I-5 if you're going to take all the data. But astronomers are very comfortable with the fact that they throw data away. I have a hard time with that, but no problem. Optical telescopes. Well, we can only use them when the sun's down, so that's half the time, and when the moon's not up, and that's half the time, and then when I'm not drinking coffee, and that's half the time. Sorry. So they're very comfortable with the fact that not all the data gets observed or doesn't get reduced. I'm sure you hear every once in a while that someone saw an asteroid that might have hit us 3 weeks ago. They discovered it 2 months ago, but didn't look at the data until yesterday. So they're very comfortable with that. And so one of these proposals is, let's go ahead. Let's throw away 90%, 98% of our data, and just put it on a truck and reduce it as time becomes available.
Okay. So as we move to new application spaces, mobility is dominating a lot of people's thoughts today. So do you think that we'll see an FPGA in a cell phone anytime soon?
So an FPGA in a cell phone, I sure hope so. Actually, we've had programmable logic devices in cell phones for quite some time. not the large FPGAs, but smaller CPLDs. And we have had FPGA wins in sort of the high-end data assistance. So really the answer to that question is yes. And the reason is actually, you have to think about the dynamics of that business. They come out with cell phones pretty darn rapidly. Yes, they're extremely cost sensitive, but on the high end, those extra little features are pretty darn valuable. And so I would expect, yeah, this is a natural extension of the temporal data processing front end to have an FPGA to do the spatial data processing on the back end, especially for these software-defined radio types of applications. Expect to see that to become rather common.
Okay. Well, sticking with applications and directions for the marketplace, what about FPGAs and robotics? Do you think FPGAs and the real-time aspects and reprogrammability are particularly apropos for robotics?
I really do, and there's several aspects of robotics where they're particularly, where FPGAs are particularly useful. First is control functions, and I sort of mentioned in passing, where do we get used? Oh, we get these bizarre control functions or unique things. Putting a little bit more intelligence into a limb, for example, is, our bodies do that, and it would make sense to do that in a robotic system as well. There's also, it's a case where you want this supercomputing. You want a custom supercomputer because you're heavily constrained. In reality, you don't really need a custom supercomputer unless you are constrained, unless you have an amount of data that's so large that you're just not going to get through it in time, or it consumes too much power, or you're space or weight limited. And all these things happen in robotics. If you have a robot, you want to be autonomous, you're constrained with power, you're constrained with space, and you have this problem that you have to do image processing or complex control processing and do that in real time. You don't get to truck that to San Diego and wait for it. Right? Your robot's got to stand up or it's going to fall down. So and there are similar applications. For example, automotive control. So gee, we would like to have automobiles with control systems so they don't run into one another, no matter who's driving or some hands-off driving. Yeah, I would like to have the most powerful supercomputer in the hood of my car, everybody else's car, when that's going on. And I think this is it's a beautiful application of spatial computing, whether it's going to be using programmable logic devices as we perceive them today, or if it's going to take maybe a word-oriented device or something else, remains to be seen. But spatial computing is a fundamental component of that. It's got to happen.
Okay, in your presentation you talked about the idea of dynamically reconfiguring an FPGA as being something fairly advanced for the industry. Why hasn't a killer app appeared so far, or has it appeared for dynamic reconfiguration, and what are the difficulties of making such an app?
Oh boy. So why don't we have a killer application for dynamic configuration? Can't think of one.
Is there a difficulty in the application design?
We do have several problems there. We don't have good simulation capabilities for something that's going to change its programming at that level, and so that makes that difficult. But what we tend to find is that the overhead for reprogramming these devices can be large. These large FPGAs, how big is the program? Well, it could be about 10 megabytes of program to load into to do something. Now, in a partial configuration, maybe you're going to get by with a couple of megabytes, or maybe a little bit less. So it takes a lot of bits to change the programming. So it takes a lot of time to change the programming. And so that puts you in a situation where if you want an application that's going to reconfigure, if you're going to avoid spending all your time reconfiguring and most of your time doing the processing, then you have to minimize that somehow. And so that leads us to small reconfigurable regions, which are small is less interesting because you can do less. But it also brings back this question, I could come back to it again, about word-wise devices. We're programming all of our devices at the bit level. If we were able to, if the programs themselves were smaller, if we could program word-wise or have some compress out the redundancy in that or somehow, that perhaps we could reduce now that configuration overhead and make some of these rapid reconfiguration applications more interesting. I should say that there have been devices that have addressed that by having a second copy of the configuration memory. So you can program one copy while you're running out of the other. But if the configuration memory makes up about 30% of your die size, which is pretty reasonable, you're adding 30% to the cost of this, or more than that for the large devices, that most people don't ever see. Gee, instead of a 30% adder for a second copy of the memory, maybe I should just make a device that's 30% bigger and have that other 30% be my reprogramming region. So these are all questions that go into the system design around what that device would look like.
Okay, thanks. I have a question about configuration because it's particularly important, obviously, for FPGAs. Most FPGAs are configured when power is applied to a system and the data comes from an external memory or perhaps a microprocessor. But if you want to get into spatial computing, and you can imagine having hundreds of bit patterns ready to configure the same FPGA and configure over time, if those bit patterns come from a network, are you concerned that those patterns could then contain viruses? Because today, a virus is data destructive. It doesn't harm a computer. But if you could be physically destructive by introducing viruses into configuration patterns, how would you handle that?
So yes, it's true. I guess you would have to know a lot about that application to know what specifically how to insert a virus. We have a similar problem that's not that's just in terms of data security or theft of the data. And so what we currently have in our large devices is we can encrypt the bit stream. So when you're sending the bit stream even over the network, it could be sent encrypted. Now somebody could tamper with that. You get something that's gibberish. We have checks to make sure that you don't actually try to execute something that's gibberish. But we do have control over that. We could prevent an intentional virus, and with the same mechanism we use to prevent theft of the design.
Okay. Staying with configuration.
Well, it's a really hot topic.
Yeah, there's a staying with
all your buddies are here.
all here. Staying with configuration, as we get to smaller and smaller geometries, the potential for single event upsets are always there. And as you mentioned, we have hundreds of megabits of configuration space. How do you handle radiation hardness for FPGAs in space applications?
So how do we handle radiation hardness? We actually have we have devices that are built with a hardened process, and we'll do specialized testing. There are a couple of other things that we do to address this problem. One is what you might think of as sort of brute force. It's relatively straightforward to triplicate. So if you want to do triple modular redundancy, we can certainly do that. And we have a tool that will do that. We'll take an application, triplicate it, and drop it onto the device. So now if you're worried about a single event upset, it's only going to hit one of your triplicated designs. Something you can do, since you have this spatial aspect of your computing, you can just make 3 copies. Something else to do, in particular, there's been a lot of concern about hits in the configuration memory. It's something that's not always obvious. That memory is controlling the operation of the device. It's always being read, right? You can't do ECC on it because every bit must be correct. If one of those bits changes, now a connection that you thought you had is no longer there. Or your lookup table now has the wrong value in it. So your logic changed. Okay, this should scare you. Okay, so what we do about that is we have a scrubbing function that we could run so the device is continuously reading and correcting errors in its own configuration memory. So that it can make a pass through the configuration memory every few milliseconds, and correct any error that might have occurred. Flag the fact that there was an error. And now you get back into how does a system handle high reliability applications. You may need to roll back your system to the last time you knew it was correct, do transactional-oriented operations like that. But so there are a couple things we can do about very high reliability.
Okay. So we talked about computing where the CPU is central to the computer or the FPGA is central. What about peer processing where an FPGA and a CPU compute together? One isn't subservient necessarily to the other. What kind of FPGA technologies are available today that allow an FPGA and a microprocessor to work together in harmony, not one as slave to the other?
So I'm going to cite this example I mentioned at one point in the talk. We're putting an FPGA in a Xeon socket, and that thing that's talking over QPI, so it's actually dealing with the same memory hierarchy your processors are. So now these things can communicate just the way you would communicate with another processor back to the hierarchy. So that's, again, this is kind of one of those system questions about how things put together, and I think leveraging an existing system that has a lot of effort gone into it is really the right way to be doing that.
Okay, well, staying on that theme, how successful has it been to put PowerPC architectures embedded inside FPGAs?
How successful? So how, judging by how well they're used, I think that has been rather successful. So in those devices, we have a very high percentage of those processors being used. It's actually kind of a funny question. So, gee, there's a microprocessor in there. Do you use it or not? Well, it turns out that it's there whether you use it or not, so you might as well use it. So we get quite a bit of use out of that. Some operations, for example, the bitstream scrubbing, can use that processor, and so and do that. We actually find there's tremendous value. I talked about spatial computing and all the wonders of that. But there's some things that's not very good at. Spatial computing is kind of breaks down with the control-oriented operations. And so putting the processor in there to do that is actually a pretty good deal. So I would say how successful? Sort of medium-high successful is what that is.
Okay. Sorry, I've got so many questions. This is excellent. We could be here for another half hour. Oh, we have about another 2 minutes, I believe.
Pick the one written in red.
Yes. Well, there's a quick one here. What's the most common product that contains an FPGA?
The most common product.
Where are they used?
Actually, probably the most. So one of the most common products was probably HD TVs have FPGAs in them, the high-end HD TVs. But probably the one you run into most often is we sell a lot of devices into data communications and telecommunications. So Cisco was a big customer, and we liked them a lot. I tell people when you make a cell phone call, your voice went through our chips. When you download a web page, the page came through our chips. In these applications, you have a huge amount of data, the small amount of processing, exactly kind of structure I was talking about. Okay, we can set up something that's going to strip out the header, determine where this goes, direct the packet to where it belongs. These are that's where most of the devices are gone.
Okay, we've got many quite technical questions, and we're unfortunately running out of time, but I'll just ask this one very last question, which is simply, how do I get started? What's the minimum development kit I need to get involved? The
minimum development kit is actually free off the web, so you go to the Xilinx website and download it from there. For a starter kit board, there's a $59 board that's sold by Digilent, and actually very popular in academia. So we have there's a huge amount of courseware and example applications and stuff built around this board. And in some ways, perhaps too successful, because the first round of professors that were great, they could give all these assignments and students did them. The second round of professors, the students went on the web to look to see if the assignment had already been done and posted. And they're just too clever. They're downloading those solutions through our chips, I guess.
Well, I'd like to thank everyone for the questions. We've got almost a centimetre thick worth of questions here, and I want to remind everyone that Steve will be available to take some questions just shortly after the end of the session. So once again, thanks to everyone for the questions and to Steve Trimberger. Thanks. Thanks, Steve.
Hey, good job, Steve.
Thanks, John.
Steve, thank you very much. I just wanted to be sure and say thank you to Steve, who's a member of the Semiconductor Special Interest Group and produced today's session. And of course, Steve, to you, thanks very much. It's just been a real pleasure to have you here. And as Steve mentioned, Steve's going to hang around and answer some of your questions. We have to let him go so he can see the Babbage engine get cranked at 2 o'clock, but if you will stick around for that. And then we have a gift for the two of you. It's our special core memory book, which is some of the best photographs of some of the best items in the collection. So thanks very much for helping us out today.
Thank you.
All right, guys, thanks. Thanks, everyone. Have a good day.
Right, thanks. So,